Hi, my name is Ian Fogarty, and I'd like to talk to you a little bit about acids and bases today. We've already looked at equilibrium, and equilibrium is going to play a large role in what we do with acids and bases. Here's an equilibrium that we haven't seen very much of, where water can split up in equilibrium with H plus and OH minus. So what that means kind of for our water molecule here is that right here between the hydrogen and the oxygen, that bond is going to break and be left with an H plus and left with an OH minus. So that's going to be a plus, and that's going to be an OH minus. So as it turns out, if you're going to take one water and split up into a hydrogen, you have to also make an OH minus. So in normal regular water, the concentration of H plus has to equal the concentration of OH minus. And that happens to be, under normal conditions, 1.0 times 10 to the negative 7. It's called the auto dissociation of water. It happens all the time and you can't do much about it. So we are used to using ice boxes in equilibriums, and so here we go. Water is a pure substance, and so we said that the concentration of any pure substance, including pure liquids or solids, was 1, and so we just would ignore this. And so then if we start out with 0 hydrogens and 0 hydroxides, because the water hasn't split up yet, we're going to gain a little bit, and we're going to gain a little bit, and we're going to end up with these two. And so, like we're used to with the equilibrium, our KQ, but in this case it's called KW, is equal to the concentration of H plus times the concentration of OH minus. Those numbers are there, and so the KW is 1.0 times 10 to the negative 14. And that's a number that we're going to come back to all the time. So here's our equilibrium again with our KW. And so we can, under normal conditions, and the water that you normally drink, we have this is equal to that, and together they create the KW 1.0 times 10 to the negative 14. However, later on, we can adjust this. So if we increase the H plus, then in order for this number to stay the same, that number is going to come down. And so in situations where the H plus is high, the OH has to be small in order for that number to stay the same. From a chemical kinetics point of view, it's very simple. It's a Le Chatelier's principle. Suppose we have an equilibrium set up, and this is going to be 1.0 times 10 to the negative 7, and this is going to be 1.0 times 10 to the negative 7. If all of a sudden we increase the number of H pluses, that means the chances of a hydrogen running into an oxygen are increased, and so then the backwards reaction can increase a little bit. Meanwhile, the forward reaction is still the same as it was, and so there will be a backward shift. And as it does that, this number, the hydroxide number drops while this is still a little bit high. So we can look at it from two ways: a Le Chatelier's principle kind of idea, or KW idea. The point is, if they're equal, then that's great. If one is high, the other one has to be low. Now, we're pretty familiar with acids. We named them in Chemistry 11. We talked about acids all the time, and the fact that an acid has H plus in it. So Arrhenius came up with the idea that acids have to have an H plus in it. And so his idea was that if you take HCl and you put it in water, you'll get H plus and Cl minus. And in fact, the HCl all by itself isn't that bad of a deal. It doesn't do a whole lot. But when you put it in water, it splits up into this H plus and Cl minus. And it's that H plus that does all the chewing that we're familiar with acids about. And so if we look at our icebox here, then we would start with 0.1 molar of this. We already had some hydrogen because it's in water, so there's some H pluses already there from the auto dissociation of water, but it's so small we usually don't worry about it. And then we have 0 chlorines. And so as this reaction happens, because it's a strong acid, and this is 100%, that means they will all split up. A strong acid means it splits up 100%. And so that means out of my 0.1 molar of HCl I start with, I'm going to lose all of them and be left with none. I'm going to gain, it's a 1-to-1 ratio, so I'm going to gain 0.1 over here, and I'm going to gain 0.1 over here. And if I start with 1.0 times 10 to the negative 7 and 0.1, I end up with 0.0.1000001, and which gets rounded up to 0.1 anyways, and 0.1. Now, here's a list of strong acids, and a strong acid means they split up 100%. There's HCl, there's HBr, there's HI, HNO3, HClO4, and the first dissociation of H2SO4. You'll notice there's still another hydrogen here that can fall off later. We'll talk about that after. If it's not in this list, then it's not a strong acid. If there are strong acids, there must also be weak acids. So here is a weak acid, a weak Arrhenius acid. This happens to be vinegar, acetic acid, and so this hydrogen kind of falls off and gives us H plus and CH3CO minus, your acetate. And so if we start filling out our icebox, if we started with 0.1 molar acetic acid, we had some H pluses from the breaking up of water already, but it's really small, so we can pretty much ignore it. And then we have some acetate, none left. Now here's the question. If this had happened 100%, it would be a strong acid. However, since it's a weak acid, that means it's less than 100%. But it could be 90%, or it could be 10%. And so if it was 90%, then it would be very, pretty strong, not 100%, but pretty strong. And if it was 10%, it would be very close at all. And so out of the weak acids, you can have weak acids, or you can have strong weak acids, and you can have medium weak acids. And so how can we tell how the strength of an acid? Well, we have our equilibrium. Ka is equal to the concentration of H plus, concentration of CH3CO minus, all divided by acetic acid, sorry. And so if we remember, this is just a KQ. And so a large KQ would mean it's mostly products, a small KQ would mean it's mostly reactants. And so here, this kind of tells us the strength. If it's mostly, but not all products, then would have a large K, in this case A, and if it was hardly any products, it would have a small k. So the Ka, which is down here, the size of the Ka tells me how strong of the acid it is. And so a small Ka means that it's a really weak acid. A large Ka means that it's a stronger weak acid. And a humongous, perhaps close to unrealistic number, Ka, means that it's a strong acid. And so here we have some examples. So here we have nitrous acid, splits up into H plus and NO3. The Ka is something times 10 to the negative 4. So it's mostly reactants. Okay. Acetic acid is even more mostly reactants, less of reaction. Down to -8 and -10. So out of these are all weak acids, but this is kind of a strong weak acid. And this is a weak acid. And so the Ka tells you the strength of the acid.